Hey, welcome. You ever stop and think about what's actually going on inside your phone? Or, a satellite flying over our heads? It all boils down to just a few basic, fundamental rules of electricity. And today, we're going to demystify them. Our guide, a university lab manual all about DC circuits. So, let's dive right in.
So this quote from the musician Robert Fripp, which is actually in our source manual, I think it just sets the stage perfectly. Begin with the possible and move gradually towards the impossible. And that's exactly what we're going to do. We're going to start with the basics, the possible, and just build up step by step. And trust me, by the end of this, you'll have the tools to understand circuits that might seem totally impossible right now.
Okay, take a look at this. I know, it might look like a diagram you'd see in a high school textbook, right? But seriously, don't be fooled. This simple little loop, it holds the secrets to basically all electronics. It's just a closed path, you've got a power source, a component, and we're about to unlock exactly what's going on inside.
All right, so before we get into the rules of the game, let's meet the players. And I mean that literally, because these aren't just symbols on a page, okay? They are real, physical things you can actually hold in your hand. So, welcome to the lab.
So on the left, that's a breadboard. The best way to think about it is like it's the canvas. It's the stage where we build and test out our circuits. And on the right, those are resistors. And their one and only job is exactly what their name sounds like, to resist the flow of electricity. They are absolutely fundamental to controlling everything that happens in a circuit.
So what is a DC circuit anyway? I mean, DC just stands for direct current. And really, it's super simple. It's just a closed path, no breaks in it, where the current only flows in one direction. That's it. Think of it like a one-way street for energy. It goes from the source, through all the components, and then right back again. Nice and steady.
Okay, now for the main event. Seriously, if you only remember one thing from all of this, make it this next part. We are talking about the golden rule, the one principle that governs how all of these parts work together. And that is Ohm's law.
And here it is. It's so elegant, so simple. V equals I times R. So V is voltage. Think of that as the pressure, the push that gets everything moving. I is the current. That's the actual flow of electricity. And R, well, that's the resistance we just talked about, the part that pushes back against the flow. The key thing to get is that these three are totally linked. You can't change one without affecting the other.
And this is where the theory smacks right into the real world. This table, it's straight from the lab manual, and it shows Ohm's law in action. So check this out. We've got a resistor that's always 1 kiloohm. See what happens? You put in 2 volts of push, you get 2 milliamps of current. Now triple that voltage to 6 volts, and look, the current triples right along with it. It's this perfect, totally predictable relationship every single time.
So, what's the big takeaway here? It's that this little formula, V equals I times R, isn't just some abstract physics concept. No way. This is the actual practical tool that engineers use every single day to control electricity with incredible precision. It's how they design, well, every electronic device you can possibly imagine.
Okay, so we've got our components, we've got our golden rule, Ohm's law. So what's next? Well, now we're going to look at the two basic ways we can actually arrange those components inside a circuit. Okay, on the left, you're looking at a series circuit. See how the components are all chained together, like links in a chain, one after another, in just one single path. But then on the right, that's a parallel circuit. And here, the whole path splits up, giving the current a bunch of different branches it can flow through all at once.
And this right here is the critical difference. This is what you really need to get. In a series circuit, the current, well, it has no choice, right? It's the exact same amount of current going through every single component. But the voltage, the push, it gets divided up between them. Now, in a parallel circuit, it's the complete opposite. The voltage is the same across every single branch, but now it's the current that splits up and divides.
So, why does any of this matter? Well, I've got the perfect real-world example for you. Do you remember those old, super frustrating holiday lights? The kind where if one little bulb burned out, the entire string of lights went dark? Ugh. Well, that's a series circuit. There's only one path, so one break kills the whole thing. Modern lights, on the other hand, are wired in parallel. Each bulb gets its own little branch, so if one goes out, the rest of them just stay lit. So much better.
All right, so now we have our building blocks, right? We've got Ohm's law, we've got series, we've got parallel. With just these things, we can do something really, really powerful. We can actually take circuits that look incredibly intimidating and just break them down into simple problems we can actually solve.
Just take a look at this thing. It's called a ladder circuit,
And yeah, compared to that simple loop we started with, this looks pretty complicated, right? You've got all these different series and parallel parts all mixed together. It really does look like a puzzle.
So the big question is, how in the world do you tackle something like this without just getting completely lost in the weeds? How can we take this really complex system and make it simple again, using just the basic rules we've already covered?
Well, the answer is this really powerful technique called Thevenin's theorem. So on the left, you've got a complex network, kind of like that ladder circuit we just saw. It looks messy. But what Thevenin's theorem lets us do is take a kind of mathematical shortcut to simplify that entire mess down into the clean, simple little circuit you see on the right. It's incredible.
And this is the really cool part. What this means is that to anything else you connect to it, that whole tangled mess on the left behaves exactly the same as that super simple circuit on the right. It's like you can replace the whole thing with just one voltage source and one resistor. And it's not magic, it's just the power of applying those basic rules we've been talking about.
Okay, let's start to wrap this up and bring it all back to the big picture. We started with the simplest little components, and now we have a way to simplify really complex networks. These truly are the building blocks of, well, everything electronic.
So, let's just do a quick recap of the key building blocks. First, a DC circuit. It's just a simple one-way loop. Second, Ohm's law, V equals IR. That's the golden rule that runs the whole show. Third, you've got your two main setups, series, where current is the same for everything, and parallel, where the voltage is the same. And maybe most important of all, we saw how you can use these simple ideas to deconstruct and understand even the most complicated-looking circuits.
You know, I wanted to share this one last thing, a note from the author of the lab manual, James M. Fiore. He says he wrote this whole thing out of frustration because he couldn't find a manual that was readable and affordable for his students. And I just love that. That passion for making knowledge clear and accessible, that's exactly the spirit we try to bring to everything we do here.
So, we started with the possible, and we worked our way up to what might have seemed impossible at first. We've basically handed you the fundamental toolkit for controlling electricity. And it's not just some abstract theory anymore, right? So I'll just leave you with this one final thought. Now that you know the rules, what could you build?